Welcome to Working with Graph Schemas. My name is Mark Selwan, a member of the product team, and in this section, we'll cover everything you need to know about getting started with creating awesome graph schemas. To start things off, let's talk about how we actually define schemas. Let's start by level setting on what graph schemas actually are in the world of Datastax Enterprise. It's important to note that graph schema is a concept introduced in DSC Graph for efficiency. Now, graph schema is a combination of property keys, vertex labels, edge labels, and the semantics that connect them. Graph schema also enables the definition of indices before the data is inserted into the system. Graph schemas is managed by the Graph Schema API that's accessible to you, the end user, via the schema object in Datastax Studio or even inside of the Gremlin console. The Schema API provides the methods such as property key, vertex label, edge label, and also supports the Fluent interface. The Schema API provides two types of schema modes that allow users to define whether they want to run in production mode or development mode. Production mode is the default and recommended mode to run as it requires you to define schema in advance upfront to make sure that you're getting the best performance possible out of your graph. Development mode allows DSC Graph to infer schema at insertion of data. While this is convenient for development, it's still recommended to use this as a tool for exploration in development environments, but you'll want to use production mode where performance and scalability are key. DSC Graph allows you to globally set the schema mode via the DSC YAML file, but it's recommended to leave it as is, defaulting to production mode. You can dynamically specify the schema mode with the syntax on the bottom here should you want to switch to development mode for testing purposes or for exploration. There are four main elements to building graph schema. In order, you must first define the property keys, the vertex labels, edge labels, and indices. Let's take a deeper look into the first three elements. Property keys are the first step in your schema definition. You can think of these as your attributes that define uniqueness, data type, cardinality, and meta properties. These attributes can then be associated with vertices, edges, however, they are independent. Here's how you typically define a property, specifically a single cardinality property key, which is the most frequently used. You can see here that we define a property key name, then data type, and then the cardinality, though single cardinality is assumed by default. Here's an example of defining a multi-property key. A multi-property key allows for many text values to be stored for a respective property. In this case, it's possible that there are multiple film production companies for a given production. DSC Graph also allows for the creation of meta properties or multiple properties within a given property key. You can see that we define a source and a date property key, each with a different data type, and we can include them inside of our budget property key. It's also worth noting that meta properties can only be used with vertex properties and can be applied single or multiple cardinality properties. Here's a list of supported property data types. As you can see, everything you'd expect is here. Everything from small ints to decimals to text, even geospatial objects. So now that we understand how property keys work, we're ready to talk about vertex labels. Vertex labels are your entities in the entity relationship model. They define the type of vertices in a respective graph. Defining vertex labels are the second step in the schema definition process. They contain the Vertex ID definition, a unique label, as well as the associated property keys we already defined in step 1. Thinking about the Vertex ID is really important. There are two types of Vertex IDs in DSC Graph, user-defined IDs and system-generated IDs. User-defined Vertex IDs are the recommended approach as they are much more performant and give the user the ability to control graph partitioning. System-generated Vertex IDs are to be deprecated and have performance limitations with larger graphs. So let's dive into user-defined Vertex IDs. They're defined via two components: the partition key, which a vertex belongs to, and a clustering key, which helps uniquely identify a vertex within a partition. This may sound familiar because these are the exact same concepts taken out of data modeling with CQL. As such, the partition key is defined as a non-empty set of property keys, and a clustering key is defined as a set of property keys which can be empty. Both can be made up of single or composite property keys. Now that we understand how Vertex IDs work, let's create our Vertex labels. Remember, step 1 is to define our property keys, in this case, our user ID, age, and gender, all of which are single cardinality. Then we define our vertex label. We're creating a vertex label called user, that's our entity, and we're defining our partition key as our user ID property. Then we define other properties or attributes that are associated with our user, in this case, age and gender. The resulting graph partitioning may or may not make sense depending on the types of traversals you require for graph. For example, it would not be the best partitioning strategy for traversals that analyze all users within a particular age. On the other hand, this partitioning strategy does work well for queries that retrieve one user at a time by a known user ID. Let's take a look at another example. This time, we'll be defining our movie vertex label. Notice how we have two properties, year and country, as our partition key. This is known as a composite partition key, as we're combining two or more values to define data locality. It's important to remember that just like in SQL data modeling, you must always provide both values of a composite partition key when querying back the data. Now, because a movie might have multiple releases or versions defined by year and country, we're going to use movie ID as our clustering key to define uniqueness for a given movie. The data model allows us to start by finding all movies for a given year and country, and then allows us to narrow down by movie ID. Lastly, let's take a look at an example that uses system-generated IDs. Remember, system-generated vertex IDs are being deprecated. So let's take a closer look. Notice that in our vertex label definition, we have not specified a partition nor clustering key. In this case, DSC Graph will generate an ID on insertion that consists of a community and member IDs. While this sounds convenient in theory, it also means that we lose all control of data locality and uniqueness. The last thing to note about creating vertex labels is that you can reuse property keys across vertex label definitions. This means there's no benefit for having a genre name or person name property. Simply define the properties associated with the vertex label, and the values of the properties will always remain local to the respective vertex. Okay, so now that we know how to define our property keys and vertex labels, let's talk about how you actually create the relationships between them. These are known as edges, and as such, we need to define edge labels as a third step in our schema definition process. Similarly to vertex labels, an edge label contains a unique label name, cardinality, associated properties, and the domain and range. You'll notice that there's no such thing as a user-defined edge ID. This is because the edge IDs are automatically derived from the vertex IDs. We'll take a closer look at that when we talk about inserting graph data. Let's talk about creating edge labels. In this example, we're creating a single cardinality edge label where a user rates a movie. In this case, we only want at most one rating between a respective user and movie, so we add single to the edge label definition. We then define our properties. It's worth reminding you that edge labels cannot have multi-properties with meta-properties associated with them. Then we define our connection. Logically, the directionality of the relationship is that a user rates a movie. So we first define the user, then the movie. Even though we define directionality this way, relationships are stored bidirectionally on disk to make traversing in and out of relationships easy. Let's take a look at multi-cardinality edge label definitions. In this example, we have a movie vertex label and a person vertex label. While person can be anyone, we're relating movies and person by the roles that they play in a respective movie. Because it's possible that a single person played many roles in a movie, we define this as a multi-cardinality edge label. Now, multi-cardinality is assumed by default, so it can be omitted from the edge label definition, as you can see in the bottom example. And here we have an example of defining multiple connections inside of a single edge label definition. We have our user-to-user connection, our user-to-person connection, and our person-to-user connection all in a single edge label definition. And remember, because edges are stored bidirectionally on disk, it's actually not necessary to create edges that go in both directions in most cases. Lastly, it's time to talk about our fourth and final step in the schema definition process, creating indices. Because there's a lot of depth to indices in DSC Graph, we'll cover them more in depth separately, but for now, know that there are three types of indices: vertex, property, and edge indices. Now that you know the schema definition process, let's talk about some ways you can find information about your schema, starting with the schema describe command. This will list all of your schema definitions. If you want to print schema elements for a specific edge or vertex label, you can simply do that by adding a describe at the end of schema.vertexLabel or schema.edgeLabel. Now, if you want to drop all of your schema definitions, you can simply run a schema.drop command, but please be careful as this will cause you to lose all of your data in your respective graph. This is a larger example of a graph schema. In our graph-related training units, we'll be relying on this KillrVideo graph schema example. The graph schema contains 4 types of vertices labeled movie, user, genre, and person, and a number of labeled edges that may connect to vertices of specific types. Study the vertex IDs and properties, their keys, names, and value types, shown in the schema graph. The edge cardinalities are omitted for visual clarity. The only multiple cardinality edges are actor and screenwriter, that is based on our specific dataset properties. There is only one multi-property and no meta-properties. Now that you've learned all about creating graph schemas, let's take what you learned and put it to good use.